card comes off the deck. The first two cards just start the two piles. After that, whichever pile is showing the bigger card, the new card goes there. Kai the puppy needs help sorting his two toy piles. Starting with the very first toy going into the first pile and the second toy into the second pile. For every toy after that, he adds it to whichever pile currently ends with the bigger toy, and if neither pile is bigger, he adds it to the smaller pile instead. I'm Kai. That card game is actually a LeetCode problem. Let's turn it into code. This is distribute elements into two arrays. You get a list of distinct numbers. One by one, you drop each number into array1 or array2. The first number always starts array1. The second number always starts array2. That gives both piles a top card to compare against. From the third number on, check the last value in R1, check the last value in R2. Bigger last value, that array gets the new number. Nums equals 2, 1, 3, 2 goes to array1, 1 goes to array2. 3, array1's last is 2, array2's last is 1, array1 wins, so 3 joins array1. Result, array1 equals 2, 3, array2 equals 1. The word distributes makes people reach for a heap or a sort step, but the rule only ever looks at the two most recent tail values. So it's a plain single pass with 2 pointers, no data structure earns its keep. Here, try sorting nums equals 2, 1, 3 first, sorted. It's 1, 2, 3 split evenly into array1 equals 1, 2 and array2 equals 3. But the real rule gives array1 equals 2, 3 and array2 equals 1 instead. Completely different. Sorting throws away the one thing this problem cares about, the order the numbers arrive in. We use plain lists here because we need instant access to the last item in each pile on every step, not a search through the whole thing. So array1 starts with the first number, array2 starts with the second. From the third number onward, we'll loop and compare. R1 at -1 just means the last item in R1, no searching needed. Whichever last value is bigger, that list gets the append. Put together, it's just seeding the two piles, then looping through the rest, comparing and appending. At the end, we return array1 followed by array2. 5 seeds array1, 4 seeds array2. For 3, array1's last is 5 against array2's 4, so 5 wins and 3 joins array1. For 8, array2's last is 4 against array1's 3, so 4 wins and 8 joins array2. Each number is looked at exactly once. Each placement is a single comparison. One pass through the list, big O of n total. 2 piles, 1 rule. Bigger top card gets the next one. First two numbers, seed the piles. Then compare and append every time. That's the whole solution. I'll be back tomorrow with another one. Stick around, subscribe. Quick quiz. Why do we seed array1 with the first number and array2 with the second before any comparing starts? Pause the video and think it through. Take a second. Think about what happens if you compare against an empty array. Both arrays need a last element to compare against, and seeding them first means we never have to special case an empty array in the loop. Round 2 for nums equals 2, 1, 3, array1 ends up 2, 3 and array2 ends up just 1. Why didn't 3 land in array2? Pause and work it out. Walk through each comparison in order. Don't skip ahead. Array1's last element, 3, was bigger than array2's last element, 1. So 3 joined array1. The rule only ever looks at the last element of each pile, nothing else. Stock is cheap. Let's actually run this. I fed it all. 2 of the problem's real examples. No cherry picking.